And there are all you beautiful people. Hello, beautiful people. So some of these videos I will show you today. Some of these videos we will skip, but you can access all of them in the resources, okay? I just want to make sure that we get through things quickly and get y'all out of here. I am going to give you guys, I will tell you when we are about 10 minutes out. And you can, if you don't have a ride of your own, you can text your ride and say, hey, I need you to come get me. All right, cool. So we are doing today gas behavior, characteristics of gases, gas laws, and molecular composition of gas. Let's roll. We are starting. Reminder what STP, not this STP, is standard temperature and pressure. Okay, in this case, when we're dealing with gases, we do it at 0. Do you remember a couple weeks ago, we were talking about enthalpy and STP, and we said it was roughly what temperature? Do you remember?
32 degrees Fahrenheit or 0 Celsius or 273.
No, that's for gases. But do you remember we were talking about enthalpy a couple weeks ago? And do you remember? It was roughly something. It was like 22, 23 Celsius, which is roughly 70-ish Fahrenheit, which is room temperature, which is lab conditions, right? Okay. So with gases, we like to do it at 0 Celsius. All right, so when the pressure of a gas is constant, so we're going to be talking about temperature, pressure, and volume. So in this one is when our pressure is constant. When our pressure is constant, Charles's law comes in. And it says that when the pressure of a gas is constant, if the temperature increases, the volume does what? Yes. Say it again. Increases. Very good. Okay. And if the temperature of a gas decreases, the volume does what, Liam? Decreases also. So when we have a relationship where if one thing goes up, the other thing goes up. If one thing goes down, the other goes down. One goes left, the other goes left. One goes right, the other goes right. What kind of proportionality is this? Directly proportional. So we call that direct proportionality. Notice the arrows. One goes up, the other goes up. One goes left, the other goes left. That is direct proportionality. If making Caitlin happy makes me happy, it does. That is a directly proportional relationship. I'm happy. Okay, great. Now, Charles's law. Calculations using Charles's law involve a change in either temperature or volume because this is when a pressure is constant. So we're messing with the other two variables, which are temperature and volume. Now, if you remember from physical science, sometimes we would have these subscripts and they would say I and F, a lowercase I and lowercase f. What was that, James? Initial and final, right? So when you see these subscripts here, it's the same thing. We're not doing math with those numbers. Those numbers tell you your initial and final. It is 1 and 2. So this is volume 1, which is your known starting volume. Volume 2, which is your final volume, or what you end up with, right? Same thing with your temperature. Obviously, we're dividing here. Keep in mind that if I took V1 over T1 and replaced it with 1 over 2, and then I came over here with V2 over T2, and I replaced it with 2 over 4, we multiplied by a constant. What was the constant?
2.
2, because 1 over 2 times 2 is 2 over 4. Do we all agree with that? Yes. Okay. All right. So, something about Charles. These are quick, so we can do these videos. So here's our man, Charles. If it will play, here we go.
Ever wondered about the fascinating life of Jacques Charles?
Have you? Probably
Born
not.
in 1746, he was a French inventor and scientist. Charles made significant contributions to the field of gas laws. He invented the hydrogen-filled balloon, a game changer. His first flight in 1783 was a spectacular success. Charles also explored the properties of gases and their behavior. Despite challenges, he continued to innovate and inspire. His legacy lives on in science and ballooning today. So, what can we learn from Jacques Charles's journey?
Oh, a lot, actually. So, what kind of balloon did he invent? Hydrogen balloon. Do we still travel around in hydrogen balloons?
No.
Why not?
Flammable.
Oh, it does what? Oh, yes.
Go boom.
But why does it work? Why does it work?
Because it's my physics.
It's less dense than the surrounding air, right? Because it's just hydrogen and it's a tiny little atom, right? And they're together, two hydrogens are a tiny little molecule. All right, this dude right here. If you don't follow this guy on Instagram, please start following him. This is Big Manny. Okay, Big Manny is British. He's a British chemist, and he is hilarious. He shows these little chemistry videos, and what's funny is he takes himself super seriously, but it's hilarious because he has very thick British accent and slang. So if you've ever heard the British people who say "in it," he says "in it" after every phrase. He also says "summit" and all those kinds of things. Like he sounds and a little bit. He's got a little touch of Jamaican in there somewhere. So anyway, he's going to demonstrate how to make a hydrogen balloon. And yes, we do have all the supplies for this here, should we ever choose to make a hydrogen balloon. And what happens with his hydrogen balloon?
Alright, cool. So I've got a balloon there and I'm gonna fill it up with hydrogen gas and then blow it up in it. Obviously, I need to make some hydrogen gas first, innit? So I've got some hydrochloric acid there and I'm reacting it with copper sulfate. This creates some green copper chloride. Then I'm gonna add some aluminium foil to the copper chloride and it's gonna react to produce aluminium chloride plus hydrogen gas. And all of the hydrogen gas is gonna be bubbled into this nice green balloon here. You're done though, we're filling up. Come on, you know what time it is. Boom, yeah, let me take it off now. Wrap that up in that, you know. And then I'm gonna tie a string to the end, innit? And then I'm gonna light the string. I'm gonna see what I go on in it. Let's go. Oh my days, we lighting up. Alright, cool, yeah. The flame is moving up the thing still. Alright, listen up here. Let's see what pops off.
Maybe I'll put it right next to you. What pops off.
Big explosion things.
I love him. Every time he puts out a new video, I'm like, oh, what's he gonna do now? He's always like in his backyard, like blowing stuff up. He's great fun. Okay, we discussed the Hindenburg. So now that, y'all, we're not gonna chit chat because we're really gonna try and move there. All right, so he just demonstrated what happens with a little hydrogen balloon when it comes in contact with the flame. Okay, the Hindenburg was a giant hydrogen balloon, and there was a spark.
As the Hindenburg airship approached its landing in Lakehurst in New Jersey, the world watched in awe. It was the largest airship ever built, and its luxurious interior and ability to travel long distances without refueling made it a marvel of modern engineering. But in 1937, as the Hindenburg was preparing to land, tragedy struck. A spark ignited the hydrogen gas that kept the airship aloft, causing a massive explosion that sent the Hindenburg crashing to the ground in flames. The disaster claimed the lives of 36 people, including passengers and crew members, and left countless others injured. The disaster signaled the end of the airship era. The development of airships for commercial passenger travel ceased. Today, the Hindenburg disaster stands as a sobering reminder of the importance of safety and vigilance in all forms of transportation.
So yeah, that's why we don't do that anymore. Yes. I believe everyone on board died. There were people on the ground that survived, but there were people on the ground that did not. So yeah, the video that I have that was with Lab, I do encourage you to watch the one, especially the one with like the modern investigation. It was really cool. It was really, really cool. They used a lot of video footage and they discovered new footage that hadn't been seen before, and they were able to use that to do some get more data. It's pretty cool. All right, yeah.
Cool. So I've got.
All right, Manny. All right, so when the volume of the gas is constant. So we were starting with when the pressure is constant. Now we're moving on to when the volume. Oh, and one more thing about ballooning. If you've never looked up videos about the dude who filled up the helium balloons and got in the lawn chair and took himself up, but it was real. No, way before Mr. Beast. This dude was like in the 80s, maybe. Strapped himself to his lawn chair and yeah, that's worth watching. It's I think he got a Darwin Award, like posthumously. Darwin Awards are what they give to people who do stupid things, you know, like survival of the fittest, like you should have died, or yeah,
Did that from Brazil, and he got lost and he died.
Well, this dude I think was in California. Yeah. All right. So when the volume of a gas is constant. Okay. So when the volume is constant, we're talking about Gay-Lussac's law. So when the volume is constant, if the temperature increases, the pressure does what? Okay. You said it's going to increase, right? Pressure increase. Temperature increase when pressure increase, and then if the temperature decreases, the pressure, Liam, increases. All right, anybody have an Instapot or another kind of pressure cooker? When you put the lid on, you lock it down, right? And then there's a little vent that you turn to close it. When you've done that, you have made your volume constant. Agreed? Nothing's going in or out. You have a closed system. You're now increasing the temperature. Now you're pressure cooking your food because your pressure has increased. That results in a much shorter cook time because it gets real hot in there, and that pressure helps break down the proteins in your food, which cooks it faster. It's also why like chicken and beef and stuff come out so tender and really good if they've been pressure cooked, very tender. So that's what's happening with your pressure cooker. So that means that temperature and pressure with Gay-Lussac's law, or what kind of proportionality are we dealing with, Xander? They are directly proportional once again. Very good. And that gives you this thing again, remember, right? Up, down, up, down, down, left, left, right, right. So when we look at this one as a calculation, it involves a change in either pressure or temperature because our volume is constant. And it looks like this. P sub 1 divided by T sub 1 is going to give you P sub 2, T sub 2. Again, we're not doing math with those subscripts. Those are just denoting initial and final, right? It's your first and second. Now, we just did this thing with the can, but half the reason I shared it is because it's just funny. This guy doesn't say Lussac, he says Lucas. So we have a Lucas, but I'll let you watch it because it's really fat, but it made me laugh because I'm like, dude, you just made a video clearly for an assignment for school and you didn't pronounce it right, but he made me giggle.
This is Gay-Lussac's law. Experiment. So you put the can on the stove and you make it hot to the boiling point of the gas inside. And then take it. Oh! Move it over. And crush the can.
Ours crushed better.
Because the pressure and the temperature change is different.
Ours did better. Good job, dude, with the baseball hat. Gay-Lussac's law. Not quite, but we tried. So his name is Gay-Lussac. Like his first name isn't Gay. He's Gay-Lucas. Like anybody that has a hyphenated. Lucas. I did it. Gay-Lussac. I did know a lady whose first name was Gay, but it had an E. G-A-Y-E. Anyway, so this is dumb, but it's great. It's one of those stupid but good things. So this is clearly somebody else had an assignment. Tell me about Joseph Louis Gay-Lussac. So who's another Frenchman? Obviously, we had Charles, who was French, and now we got another Frenchman, and he had a nice big long name. But he actually contributed a lot to science, aside from just the law. This video sort of claims that he's not celebrated or not well known. I would disagree. I think maybe he's not Einstein, and the rest of the world doesn't know about him. But anybody who's done chemistry knows that Gay-Lussac's law exists. So, but it shows you a lot of the other things he was involved in. And one of the things they're going to show you is a burette. And we're using a burette in just a few weeks. Actually, we're going to be using them a lot. And this is the only class you'll use them in. They're not in bio, physical, earth. It's just a chem thing. And they're super cool. They're coming up very shortly. Like when I said your difficult labs are coming. I love it. Nice group.
Oh,
What happened? What happened? Wait.
why did the beat drop?
Alexa, turn on Media Center. I think we had a temporary internet flow. Hold on, it'll bring it back over. I was watching that this morning. It was a good documentary. All right, let's try again. Here we go. There's your beerette. The hook is great. So he did a lot more than just your,
This is gay.
yeah, we know. This is Gay Lucas's Law. It just made me laugh. I was looking for a video of that because I didn't know if I was going to be able to get the demo done. And I find the video, and then the one I find is this kid. I'm like, this is perfect. So, all right. So you'll never forget it. All right. So when the temperature of a gas is constant. So we did when the pressure is constant, when the volume is constant. Now we're going to move on to temperature. Okay. All right. So when the temperature is constant. Now it's Boyle's law. Okay, sometimes you'll see this called Marriott's law, but typically it's Boyle's law. So when the temperature of a gas is constant, if the pressure is increased, what happens to the volume? Who said it? Colin said it. Okay, it's going to decrease. And what happens if your pressure is decreased? Your volume's going to Ridley increase. Okay, when you have a sealed bottle of soda, you have gas, get it together, gas dissolved in the liquid, correct? Everybody agrees you've got gas dissolved in the liquid. Okay. And then when you open the cap, what do you hear? What happened? Yeah, you've got gas escaping because now you have expanded the volume. So when you expand your volume, your pressure inside that's keeping the gas dissolved in the liquid has decreased, and now you see the bubbles, right? That's what's happening. All right, now that means that for Boyle's law, volume and pressure have what kind, Jordan? Inversely proportional. So in this case, if one goes left, the other goes right, right? If one goes up, one goes down. If one goes down, one goes up. If one goes right, one goes left, right? All right, so inverse proportionality. So that means that our formula is going to be a little different. When we were talking about things that were directly proportional, we had a division equation, right? So calculations using Boyle's law involve the change in pressure and volume from known starting points. It says whoops, I just got that, of P1, V1. So again, we're not doing math with the subscripts. They're there to denote initial and final, but we're multiplying for Boyle's law. We've divided for the other two. So here's Boyle. He has a great wig. This is classy wig, right? This is like, come on, load it. I want to click. There he is.
Robert Boyle is known as an important scientist of the 17th century. Boyle, one of the founders of modern chemistry, is recognized for his studies on the behavior of gases, playing a significant role in the development of gas laws. Additionally, Boyle formulated a fundamental principle explaining the relationship between pressure and volume, known as Boyle's law. Boyle also contributed to the development of many important scientific instruments, such as the alcoholometer. His works laid the foundations of modern chemistry and greatly contributed to the advancement of science.
Yay for him. Okay, the second, yeah.
Was it even created by AI and the
Probably.
description?
Okay, the second one I'm including because it gives you a different perspective on Boyle. So we've talked about this before, but a lot of the great scientists of history, people who have, Drew, scooch up, he can't get by, there you go. A lot of people who have made contributions that we still consider very important or transformative to the way we thought about things, fell into one of two categories. They tended to be either independently wealthy or
Well,
very religious, like monks or priests. And why is that? Because people who are independently wealthy or who are monks or priests, what are they doing, James? What? Nothing. Exactly. They have lots of time on their hands. Gabe. So they have a lot of time on their hands. If you're independently wealthy and you have people working for you, you have lots of time to run science experiments and think and read and do whatever, right? But if you're a monk or a priest or somebody who's independently wealthy, you have a lot of time to do that stuff too. One of our better known in earth science or physics, Galileo Galilei, was a very, very devout religious man. And if you know anything about Galileo's history, what was Galileo known for? Like, what's the big thing we know him for? Caitlin?
Saying that the Earth was not in the middle of the solar.
Yes,
system,
yeah.
and that
Galileo's
the-
like,
that went against.
it went against the teachings of the Catholic Church, which at the time kind of
They
ran
didn't
everything.
like that.
They didn't like that. But does anybody know, where did Galileo fall? Was he a person of faith or not? He was. His daughter was a nun. And there's actually, we preserved to this day are an entire series of letters of exchange between him and his daughter, where he went back and forth about how the things he was discovering, he didn't think they were anti-faith. He thought they enhanced faith, rather the opposite. So that's why I'm sharing this about Boyle. You'll find this with a lot of scientists. Next year, we'll be talking about Gregor Mendel, who's one of the best known scientists in biology. We attribute a lot about, we know about genetics to Gregor Mendel. He's a monk. He spent his time growing peas. And those peas were essential to the way we understand genetics. So in this case, we have Boyle, who has a position for faith and science where he considers them not at odds. To this day, you will find people that fall in three camps: sciencey people who find religion at odds with science, religious people who find science at odds with religion, and plenty of people in the middle who go, no, one enhances the other. So you fall wherever you fall. Personally, I fall in that middle group. I think one enhances the other entirely, but that's my opinion, my personal opinion. Yours, it can be whatever it wants. But you should know this about him because
Something people don't know.
it does explain his perspective.
He revolutionized both science and faith. Born in 1627, Robert Boyle wasn't just any scientist. He's the bloke who gave us Boyle's Law, the foundation of modern chemistry. But here's the twist. Boyle was also a devout Christian apologist. He believed that studying the natural world was a way to glorify God. His pioneering experiments in chemistry weren't just about discovering how things work, but also about understanding the Creator's grand design. Boyle argued that science and faith are two sides of the same coin, each enriching the other. Thanks to him, we've got a legacy that blends curiosity with spirituality. So, next time you think about the divide between science and religion, remember Robert Boyle, the man who bridged that gap with brilliance and belief.
So he's another guy that can fit into that group, and there are plenty of them. And this is an example of Boyle's Law inside your body.
Pulmonary ventilation, or breathing, is induced by changes in the volume of the lungs and the air pressure within them. During normal inhalation, the diaphragm and external intercostal muscles contract and the ribcage elevates. As the volume of the lungs increases, air pressure in the lungs drops below atmospheric pressure and air rushes in. During normal exhalation, the muscles relax, the lungs become smaller, pressure inside them rises, and air is expelled. Boyle's Law explains this relationship between volume and air pressure. An increase in the volume of a container lowers the pressure of the air inside. A decrease in the volume raises pressure in the reduced space. The body's demand for more oxygen can change normal breathing to forced breathing. Additional muscles increase the changes in volume of the thoracic cavity so that more air can pass in and out more rapidly.
Okay, so if you didn't know it, that's how it works. Now, who's conscious of how they're breathing right now? Everybody's like, usually that's autonomic. Your body just does it, but that's what's happening. All of your intercostal muscles and your diaphragm are contracting, which is creating more space, which increases the volume capacity of your lungs, which creates a vacuum and sucks air into your lungs. And then when you relax all those muscles, it decreases that volume capacity and it pushes that air back out for you. Now, obviously you can force inhale, or exhale, but that's how it's working on its own. Yeah, we know, Boyle. All right, now, what happens when we combine the three laws that we just had? So we've got Charles's Law, right? We've got Gay-Lussac's Law, And we've got Boyle's law. Now I'm gonna let you predict. If we were to create an equation over here to put all of them together, what would be on top? What would be on bottom? How would it look? Anybody want to guess what would be on top? What would be on top? We have division obviously involved. What's going on top, Jordan? Temperature? Anybody else want to guess what's going on top? So if we put them all together, look, it makes perfect sense when you look at it. Do you agree that V and P are on top of every one of these equations and not on bottom of any of them?
Yeah.
This is a 1, obviously. This is on top, right? If there's nothing above it, it's on top, right? And then what's down here? Temperature. Temperature's on the bottom in every equation that it's in. Do we all agree? So when you put them together, this is what you end up with, right? So that's a combined gas law. And that's important because when you put all these laws together, you can make some pretty decent predictions about what's going to happen. Everybody could predict that when I started blowing into that balloon inside the flask, it wasn't going anywhere, right? It wasn't going to expand very much, not beyond the size of the little container area that it was in. It wasn't even going to be able to push down into the bottom of the flask because there was air there, right? We couldn't get the air out. We couldn't compress it much more than that. But everybody was pretty much figuring out that once I heated the water and put it in the bottom and then cooled it down, that balloon was going to inflate to some degree. And that's because you understand when you put them all together, that's what you get. But what's the constant? So again, a constant is if you multiplied, like we said, if you multiplied 1/2 by 2, you're going to get 2/4, right? So if you multiply, you get a constant, and we have to give that constant now a variable when we do problems. So we're going to call it K. All right, K for constant, because that's how constant is spelled. And you're going to end up being very simplified here and saying V over T equals K, P over T equals K, and PV equals K. And that's how we're going to get to K. So in this case, it's going to be P times V over T equals K. That's how we get our constant. Why does all that matter? All that matters because it's bringing us to this equation, which is one of these keep it in your head equations. This is one that will come back in any college chemistry course you take. It may show up in physical science courses. This is the ideal gas law. PV equals nRT. People remember this by saying Pivnert, which is ridiculous. My husband loves to say Pivnert. Anytime there's something that happens, he sees something, like he watches rockets or whatever on video. He sees something happens. He's like, oh, Pivnert. Like, but he's a dork. So that's why I love him. So Pivnert, PV equals nRT. In this case, we're going to break this down and show you what it means. But we also have to understand what an ideal gas is. So an ideal gas is a conceptual approximation that helps us predict the behavior of real gases. What the heck is a conceptual approximation? What's meant by that? Jordan?
It's a theoretical gas.
It's a theoretical gas. It's an imaginary gas. It doesn't exist. Well, why doesn't it exist? Because it has certain rules. And one of the rules is that ideal gas molecules do not attract or repel each other. Does it happen with real gases? Molecules are going to attract and repel each other, right? So obviously this is theoretical. That can't be. And this one, if this isn't a dead giveaway, ideal gas molecules take up no volume. That can't be, right? But the reason we set these standards is because there are so many variables that we can't do these calculations and predictions without creating this ideal gas as a standard. So we can use this to predict what's going to happen with gases. So if we break down this ideal gas equation, which is here's our Pivnert. Oh, isn't it cute, Pivnert? It's when we've combined these three again, but this time, I mean, these two with this third one, Avogadro's law, which we haven't quite come to yet. So which one is missing here? Boyle's law, Charles' law, Avogadro's law. What's missing? Gay-Lussac is missing, right? So in this case, we've replaced Gay-Lussac with Avogadro's law, and it gives us our ideal gas law. So what we have here, these are our variables. Whoops, P is pressure. V is going to be what, everybody? Volume. Okay, what's N going to be? Anybody know? What do you think? Number. There we go. It's our number of particles or our amount in moles. There we go. N is number. Like you hear people say, oh, he annoys me to the nth degree. Number, whatever number, multiplied. That's what that means, right? Just some number, some amount. What is R? Okay, this is the tricky one. R is the ideal or universal gas constant, which is equal to the product of the Boltzmann constant and the Avogadro constant. Blah, blah, blah. All right. We're going to come back to R. All right. There's R's complicated, but it's not that complicated. What is T, everybody? Temperature. Okay. Now, our ideal gas equation, what the heck is R? All right, let's see what R is. This dude is going to explain R real clearly for you. And it should make sense. All right. Do we have a commercial? Okay, David
So
Vandenbouw.
students always ask me, which value of R do I use for this problem? And I say there seem to be many, many, many different choices. And the answer is there's really only one value for the ideal gas constant, but it has lots of different units. It is a universal constant. It's pressure times volume divided by the numbers of moles times temperature. So the value for R that you get is going to depend on what units you have for pressure, what units you have for volume, what units you have for moles, and what units you have for temperature. Almost universally in chemistry, we stick to the same value for units of moles. And we've agreed on what the definition of Avogadro's number is, and a mole is the number of particles that are in 12 grams of carbon. For temperature, we're always going to use absolute temperature, and we're going to stick with units of Kelvin. But no one can decide what the units for pressure should be or the units of volume should be. And so as a result, for pressures, we have atmospheres, we have bars, we have torr, we have millimeter of mercury, we have pounds per square inch, we have other crazy ones that we can dream up. Volume, almost always in liters, but it could be in cubic decimeters, could be in cubic meters, cubic centimeters, could also be in gallons or bushels or other absurd units. And so depending upon what choice of units you have in the problem, you're going to have to pick the correct units for R. So for example, if you had pressure in atmospheres and volumes in liters, it'd be 0.8206 liter atmospheres per mole per Kelvin. But if you had pressure of bars, it's 0.08314 liter bars per Kelvin. Or alternatively, maybe you have Pascal cubic meters, then it's 8.314. And so the answer to which is the correct one, it's the one that makes the units work for the pressure and the volume that you're working with.
So your R is different depending on what units you're dealing with, right? Mm-hmm.
Can you just replace R with PV over
Well, that's how you get R, but you still need, a lot of the times R is what you need. Like you don't have it and you need to find it. So you just need to use the correct unit is what he's saying. So let's see. Ideal gas equation values for R. So here are some values for R that could possibly be used. Oh, these are all fun, right? There are lots of things you can use is the point. Depends on what you need. Now, we have another law from our buddy Gay-Lussac, and this one is combining volumes. This is the only one we didn't demonstrate in lab today because it's kind of hard to demonstrate this one. This one's more of an easy concept to just kind of understand, but it's basically this. When gas, guys, when gases combine at constant temperature and pressure, the volumes involved are always in, what do we say? Simple ratio of whole numbers. So basically, if you have 2 volumes of hydrogen and then you add 1 volume of oxygen, you're going to end up with your 2 volumes here because this is how they go together, 2 and 1. It's just basically saying if you combine them, you just add them together, and it's simple ratios. It's nothing crazy, nothing gets weird proportionality or whatever. And then we have how moles relate to volume. So this is where our buddy Avogadro comes back. You know how he loves his moles. So if the amount in moles is increased, what's going to happen? And this isn't a flexible container. What's going to happen to the volume, Xander? It's going to increase, okay? And then if the amount of moles is decreased, what's going to happen to the volume, Caitlin?
It'll.
Your amount's decreasing, so your volume's going to decrease. Yep.
Yeah.
And then at the same temperature and pressure, gases at the same volume contain the same number of moles. Yeah, particles. So in this case, what he's showing you is these balloons all have the same volume, which means they all contain the same number of molecules. So if you have a hydrogen filled balloon or a nitrogen filled balloon or an oxygen filled balloon and they have the exact same volume, the number of molecules is the same. And that has to do with the size of the molecules, which when you think about it, makes sense, right? Makes sense? Huh?
Different gases have different densities at the same temperature.
Right. Different gases, but this is at the same temperature, right? So say it again. Different gases have different densities.
Right?
Yes.
At the same temperature, like two different gases could have two
The
different
densities will be the
Is that-
same.
is that necessarily true?
The densities are the same, but your number of molecules, I mean, densities are different, sorry, but your number of molecules is the same. And that has to do with how they act, how they move, and how big they are, how big the actual molecule is. So this is what Avogadro says about stuff. And basically the main thing there is your flexible container, right? If you add more particles, it's going to grow. So what about amount and volume, Xander? They are directly proportional. So far, Boyle is our only indirect, right? Everything else is directly proportional. So here's our Avogadro's law, again, as a calculation. You guys saw this over here. Some of you noticed, oh, look, it's the same color. I tried to cue you in. So calculations using Avogadro's law involve the change in volume and the amount from a known starting point of each. So again, you're not doing math with the subscripts. They're just telling you. And this is your volume 1 number of particles or number of moles, right? And if you multiply them by whatever your constant is, you're going to get your answers for your final. All right. Now, this guy's talking about Boyle's law, Charles' law, and Avogadro's law together, which we know made our ideal gas law, right? When we put them all together, that's what we got. 12.
In society, we have to follow laws that maintain order. Did you know all chemical matter follows certain laws as well? In fact, we can describe those laws by looking at relationships. Some easy laws to begin with are the ones that govern the gases. Back in 1662, Robert Boyle realized that gases had an interesting response when he put them into containers and changed their volume. Take an empty bottle and put the cap on it, closing that container. Now squeeze your bottle. And what happens? The pressure inside the bottle increases when the size of the container decreases. You can only crush that container so much until the gases inside push back on your hand. This is called an inverse proportion, and it changes at the same rate for every gas. Boyle's law allows chemists to predict the volume of any gas at any given pressure because the relationship is always the same. In 1780, Jacques Charles noticed a different relationship between gases and their temperature. If you've ever seen a hot air balloon, you've seen this law in action. When the balloons are laid out, they're totally flat. Instead of blowing the balloon up like a party balloon, they use a giant flame to heat the air inside that envelope. As the air is heated up, the balloon begins to inflate as the gas volume increases. The hotter the gas becomes, the larger the volume, and that's Charles' law. Notice this law is different from Boyle's. Charles' law is a direct relationship. As the temperature increases, the volume increases as well. The third law is also easily demonstrated. When you're blowing up party balloons, the volume increases. As you're blowing, you're forcing more and more gas particles into the balloon from your lungs. This causes the balloon volume to increase. This is Avogadro's law in action. As the number of particles of gas added to a container are increased, the volume will increase as well. If you add too many particles, well, you know what happens next. Laws are everywhere, even in the tiniest particles of gas. If you squeeze them, the pressure will increase as the particles are pushed together. Low volume means a high pressure because those particles push back. As the temperature increases, gases move away from one another and the volume increases as well. Finally, if you add gas to a closed container, that container's volume will expand. But be careful not to add too much because otherwise, you could end up with a burst balloon.
So that's all of them together. Go, move on. Ooh, okay. So now we have Dalton's law of partial pressures. Okay, so this one we couldn't really show too much in lab either, but this one makes sense too, just kind of like our Gay-Lussac's law of combining volumes. So basically here, what we're saying is that total pressure exerted by a mixture of gases is equal to the sum of what? What's it gonna be? What do we think? PJ?
Some of the pressure.
Yes, the sum of the partial pressures of the gases in the mixture. And if the temperature and pressure are constant. So if you're not changing the temperature and the pressure, every gas that is a part, we're calling it a partial, part of it has a pressure. So therefore we're calling it a partial pressure. And when you add all the partials up, you get a total. This makes sense, right? Pressure 1, pressure 2, pressure 3 together is going to equal your pressure of the mixture, right? That's easy. That one's really easy. Now we get our buddy to explain why it works this way.
Yeah.
Our friend, our favorite Greek professor.
I'm so excited about it.
Oh, well, first we get a video. Hey, Marcus. Good for you. Get your MD. That's awesome. Oh, workout. Workout.
Yeah.
Work it. Work it.
Professor Dave here.
Woohoo.
Talking about Dalton's law. He knows all about the science of Professor Dave explains. We've learned a lot about ideal gases and some of the laws that describe their behavior. But up until now, we have been examining the relationships between the variables that pertain to an individual sample of gas. But a lot of samples of gas involve mixtures of different substances. So we will want to learn about how these gaseous mixtures behave as well. If we take two different gases and mix them together, will there be any new properties that can be observed? What will be the total pressure? It is the case that as long as these gases do not react with one another, the pressure that each gas exerts in a mixture of gases is specific to the amount of that particular gas that is present. And we will call the pressure of that particular gas its partial pressure. In order to find the total pressure of the vessel, we will simply add up the partial pressure. This is stated in Dalton's law. When you think about it, it makes perfect sense, since pressure is just the force exerted as particles strike the sides of the container. So the pressure from all the particles of one gas plus the pressure from all the particles of another gas should add up to be the total pressure for all the particles, assuming we are treating these as ideal gases where their identities are irrelevant. We can also make statements about the partial pressure of each individual gas as they relate to something called the mole fraction of that gas, which is a measure of the number of moles of a substance compared to the total moles of matter present. And the partial pressure of a gas within a mixture will be equal to the mole fraction of that gas times the total pressure. So if there were 0.25 moles of a particular gas out of 1 mole of total gas particle, that would mean a mole fraction of 0.25. And if the total pressure of the sample was 800 torr, the partial pressure of the gas in question would be 200 torr. Again, this makes sense on the molecular level when we consider individual collisions occurring between the particles and the sides of the container, and the fraction of these collisions that is represented by any individual substance. To see this demonstrated, let's say we capture a sample of Earth's atmosphere at sea level. We know that there will be several different gases in the sample, as the atmosphere is comprised of nitrogen, oxygen, and argon in roughly these quantities, plus trace amounts of a bunch of other things. And the sample as a whole exerts a pressure equal to atmospheric pressure, or 1 atmosphere. But what contribution to this total is provided by each component of the gas? Recall that Dalton's law says that the sum of the partial pressures of the component gases in a mixture will be equal to the total pressure. That means that if we pretend the atmosphere is comprised of only these 3 gases, the partial pressure of nitrogen plus the partial pressure of oxygen plus the partial pressure of argon will add up to atmospheric pressure. But how do we calculate the partial pressure of each gas? Well, again, the partial pressure of a gas is related to the mole fraction of the gas, or the fraction of the mixture that gas represents by number of particles. This means we can take these percentages and divide them by 100 in order to express them as mole fractions. And then we can multiply each mole fraction by the total pressure to get the partial pressure of each substance. So it's quite simple to calculate the partial pressure of each gas in our sample. And we can see that these do add up to a total of 1 atmosphere, just as the individual percentages add up to 100%. We can do trickier calculations as well by including other gas laws. Let's say we have quantities in moles of a few different gases, and we place them into a vessel of known volume and at a known temperature. We could then use the ideal gas law to solve for the total pressure. And then, if we calculate the mole fraction of each gas, we could combine this information to find the partial pressure of each gas. So Dalton's law is quite intuitive when you think about it, but it allows us to do important calculations regarding the partial pressures of individual gases within a mixture. Let's check comprehension.
And we're not going to do the equation, so I don't know if y'all noticed, but his the ink on his left arm was really apparent in this video. There are people all over the internet who wanted to know what it was, so he actually made a YouTube video explaining his tattoo. So if you're interested, just go into YouTube and put in Professor Dave's tattoo and it will pop up and it'll explain it to you. It's about space travel, I think. It's really kind of cool because he's a great nerd. I love him. Anyway, Graham's diffusion and effusion law. Okay, now we have a whole different law about gases, but this has to do with how gases move. So first, let's explain diffusion and effusion. So while both terms relate to the movement of gas molecules, effusion refers specifically to a gas escaping from a container through a tiny opening into a vacuum, while diffusion describes the gradual mixing of gas molecules throughout a space, spreading from an area of high concentration to low concentration without specific opening involved. Essentially, effusion is more focused escape through a small hole, while diffusion is broader mixing process throughout a space. If you smell your mom baking cookies, it's diffusion, right? If somebody walks in a room wearing perfume and you're like, ooh, I smell that across the room, that's diffusion, right? Effusion has to do with a specific opening. All right, let's see. Whoever's tapping, please stop tapping. My mother sits down there and listens to your tapping. All right, so Graham's diffusion effusion law, the rate, Graham found experimentally that the rate of effusion of a gas is what kind of proportional to the square root of the mass of its particle? Whoa. It's going to be inversely proportional to the square root of the mass of its particle. That's fun. And how about the rates of diffusion of different gases are going to be inversely proportional to the square roots of their mass densities? What the heck does that look like? Well, it looks like this. So rate 1 is the rate of effusion for the first gas, the volume or number of moles per unit time. Rate 2 is the rate of effusion for the second gas. M is the molar mass of gas 1, that's N sub 1, N sub 2 is the molar mass of gas 2, and you end up with that fun equation. Yeah, that's a fun one. It's an intuitive equation when you look at it. We won't be doing much with it. No, it's a thing. It's a thing, but no, it's a thing, right? We won't be doing a whole lot with it. All right. Yep, that's what it's called. And it's Crash Course and it's great. And I'm watching our time, so I think we're good. This one's a longer one, but we should, I think we may watch.
And create a space you'll love.
How about I do this? I'm going to skip it and we can come. Well, why don't you watch that one on your own? I'm watching the time and I'm trying to get you guys moving. And that one's about 11-minute video, but watch it. It's great. It's really good. It's worth it. So to review, we have Avogadro's law when we think about the balloons, right? How about this one is going to be Dalton's law of partial pressures. We had Graham's diffusion law. We've had Boyle's law. We've had Gay-Lussac's law. We've had Charles's law and an ideal gas law. And lastly, Gay-Lussac's law of combining volumes. So we had a lot of gas laws here. Okay, wait a minute, listen. If you don't drive yourself and you wish to leave early, text a parent and give them a 10-minute warning now. We'll give you a second to do that so that we don't lose you in this process here. And then what we'll do is we'll go back and I'll play that video after we've gone through this stuff. And if you want to leave, you can. If you want to stick for the 11-minute video, you may. So this is a 10-minute heads up for anybody who's trying to get out early. So far, the forecast is looking good. I've checked it like every time we've had a 2-minute video, but you never know. They really don't know. It went in 15 minutes. It went from 60% precip in the 12 o'clock hour to 15% precip. And that's a big change. So, all right. Somebody want to define a Newton for me? What's a Newton? All right, PJ.
SI unit of force.
Yeah, it's an SI unit derived for a measure of force. 1 Newton is equal to the force needed to accelerate a mass of 1 kilogram, 1 meter per second per second. So some of you are going to remember that from physical science. How about pressure? All right, what you got for me, Xander? Yes, it's a force applied over an area or force divided by an area. Force of all gas particle wall collisions divided by an area. If you're speaking about how gases react with pressure, all gases exert pressure. It is one of the fundamental measurable qualities of this phase of matter. How about a Pascal? What's a Pascal? All right, Colin. It is an SI unit for pressure, correct. Pressure or stress of 1 Newton per square meter, which is equal to 1 Eckaspar times bar, blah, 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 or dynes, you can say. There's lots of ways to come up with Pascal. Pascal is your SI unit for pressure. Do you guys remember the Blaise Pascal rat from physical science? Yeah, you remember the little French rat? He was super cute, right? Okay. All right. STP is, Caitlin?
The temperature of 0 degrees Celsius and the pressure of 0.1 atmosphere.
Well, 1 atmosphere, right? So standard temperature and pressure, 0 Celsius, 1 atmosphere. What is an ideal gas? Oh, Andrew, was that your hand? No? Oh, Addie. There you go. Ideal gas is a hypothetical gas composed of molecules that follow a few rules. They don't attract or repel each other. The only interaction between ideal gas molecules would be elastic collision upon impact with each other, or an elastic collision within the walls of a container. What is it? Is it a bug? Yeah. Oh God, those are those invasive ones, those brown marmorated stink bugs that they got into everybody's house a couple years ago. They like, if you just leave him alone, he's fine. Don't step on him because that we'll all regret it. So just leave him. I'll come get him when we're done in a minute. All right, diffusion. Who wants to define diffusion? Andrew. Yeah, from area of high concentration to low concentration. Happens in liquids and gases because their particles move randomly from place to place. Diffusion is an important process for living things. It's how substances move in and out of cells. We'll be modeling this next year. Jordan, what's effusion? Right, it's the passage of gas through a small opening or a small hole. Graham's law states the diffusion rate of a gas is inversely proportional to the square root of its mass of its particles. All right, Addie, you want to give me partial pressure? Yep, pressure of each gas in a mixture. In a mixture of gases, each constituent gas has a partial pressure, which is the notional pressure of that constituent gas if it alone occupied the entire volume of the original mixture at the same temperature. Partial pressure of the gas is a measure of thermodynamic activity of the gas's molecules. Yes. All right, labs, rats, unit 6, test study topics. What do we have? Here we go. Now, remember, Unit 6 goes all the way back to the other side of winter break, right? It's not just since we came back. Question? Yeah, we'll take care of it. Don't worry about it. Ozzy would just want to eat it, and which is not good because they smell so bad. They're terrible.
It tastes good though?
I'm assuming if they taste like they smell, they're not very good. So this, of course, will be in your resource folder, right? That's where you can access this stuff. All right, so what I'll do now is I'm going to go back. It's not the end. Hang on. I'm going to go back to that video and let it start playing. If you want to leave, you may leave. If you're waiting for your ride, you may wait on your ride. But I do ask that if you leave quietly because this is cool to watch. So like if your mom shows up while you're watching or whatever, you can step out. Just step out quietly. Of course, we got a commercial.
Welcome to another edition of Crash Course today.
What is that smell?
Oh, thanks for the rotten eggs. Who is this? Why are we doing this? I mean, are we going to be using this to illustrate some kind of scientific principle? Because we probably could have like used like some lilacs or something that wasn't egg. So like we're saying, I can smell it when I'm this close, but if I were farther away, I couldn't smell it. Now eggs produce hydrogen sulfide when they start to go bad, which smells like sulfur. That's what we think of when we think of the sulfur smell. It takes time for the molecules of hydrogen sulfide to make their way to my nose, because obviously gases don't travel from one place to another instantly. It takes some time since, as we've learned over the past couple of weeks, gases have real life constraints on how they move here in the non-ideal world. These are the rules that determine, say, how fast a leaking tire goes flat, why helium balloons don't last forever, and of course, how, where, and when we smell stuff. One key to understanding the behavior of a gas is its velocity. That is the speed and direction that it moves. And that depends on a few important physical factors. You ready to learn more? Let's do it. That smell is coming from the eggs, isn't it? So, velocity of the gas. What does that even mean? I mean, it's easy to understand the velocity of a car. You can find the velocity by dividing the distance that the thing traveled by the time it took to do it, and then tell what direction it's going, and then you're done. But the velocity of gases is harder to describe because they move in more than one direction at a time, and the overall shape and volume of a gas cloud can change constantly. To understand gas velocity, we have to know what factors affect it and how. As you might have guessed, there's math associated with this. There are two ways of studying and talking about gases. First, we can consider them as a collection of atoms or molecules that act together as a system. When we do that, we often talk about the net velocity, or how fast a sample of gas moves from one place to another, like the rotten egg smell wafting its way to my nose. At other times, we focus on the individual atoms and molecules that make up the gas. In that case, we use the average velocity of each of the particles. That's the statistical mean of the speeds of all the individual atoms or molecules in the system. There are always faster ones and slower ones, but it all evens out in the mean. The net velocity of a gas in any one direction will always be lower than the average velocity of its molecules because the overall motion of the gas is hindered by collisions among the individual particles. As with most things in chemistry and also in life, how a gas moves is more complex than it at first appears. The individual particles in a gas never move at exactly the same speed or direction for very long. Instead, they bounce around like crazy, bumping into the walls of the container and each other over and over. It's sort of like a group of kids in a hallway. They may be moving fast individually, but they bounce around a lot and get sidetracked. They always make it to the lunchroom eventually, but the group's overall speed is lower than the speed of any individual kid. So, what makes a gas move faster or slower? Well, we already know that gas atoms and molecules move faster when the temperature increases. We can understand why that happens by remembering what temperature actually is. Temperature is a property of matter that is proportional to the average or mean kinetic energy of all the atoms or molecules in the system. We sometimes think of temperature merely in terms of measuring hotness, not that kind of hotness, the hotness or coldness of a material, and it is related to that. But when you get right down to it, temperature is really just a way of expressing average kinetic energy. The reason a stove burns you is that the fast-moving particles of the burner make the particles in your hand move so fast that they tear apart your cells and tissues. It's just a transfer of kinetic energy. And what does kinetic energy have to do with velocity? Everything. And it also describes the relationship between a particle's velocity and its mass. So a good understanding of kinetic energy will help a lot as we study the motion of gases. So first, the formula for kinetic energy is 1/2 mv squared. And as you can see, any changes in the kinetic energy are directly linked to changes in velocity. If we rearrange the formula, we find that the velocity of a body equals the square root of 2 times the kinetic energy divided by its mass. This little math exercise highlights 2 important points. One, because the mass is in the denominator, we can tell that it is inversely proportional to the velocity, meaning that bigger masses move more slowly than smaller masses that have the same kinetic energy. And 2, the velocity is proportional to the square root of the mass, meaning that a fairly large change in mass is required to make a significant change in the velocity. So now we can show how the velocity of a gas relates to both its temperature and therefore its average kinetic energy, and also to the mass of its particles. But how do we put that all together? This is where the Scottish chemist Thomas Graham comes in. In 1846, Graham published his research on the motion of gas particles, which he did by passing gases, if you will, through a porous barrier. The process by which gases travel through an orifice or opening is known as diffusion. Graham was interested in how fast the gases pass through the barrier. This is called the rate of diffusion, not the velocity. It's because here we're measuring the amount of gas that passes through in a given period of time, not the distance that it moves in that time. We might measure amount in terms of moles or in terms of volume, but the rate of diffusion never uses distance. One more thing before we move on, don't let the symbols confuse you. Notice that lowercase v stands for velocity and capital V stands for volume. The perils of symbols.
Refresh the new Opera GX, the browser that puts you in control.
Yeah, everybody's gonna leave Google for whatever that is now.
Thomas Graham measured the rates of diffusion for various gases, and his results fit perfectly with what we already know. The more massive a gas is, the more slowly it moves. From his observations, Graham developed a formula, now known as Graham's law of diffusion, for comparing the rates of diffusion of different gases. It states, under identical conditions, the ratio of the rate of diffusion of gas A to the rate of diffusion of gas B is equal to the ratio of the square root of the molar mass of gas B to the square root of the molar mass of gas A. It is a mouthful, but it really just confirms what we deduced earlier. The rate of motion of a gas is inversely proportional to the square root of its mass. For example, if it takes 4.5 minutes for 1.0 liter of helium to diffuse through a porous barrier, how long will it take for 1.0 liter of chlorine to diffuse under identical conditions? All we need to figure it out is Graham's law. Let's make the helium gas A and chlorine will be our gas B. First, we have to find helium's rate of diffusion. In this case, we're using volumes with a capital V. So for helium, 1.0 liter in 4.5 minutes gives a rate of 0.22 liters per minute. So we plug that into the main formula. Chlorine gas has a molar mass of 2 times that of atomic chlorine, 35.5 times 2 equals 70.9, and helium's molar mass is 4.00. Put those numbers in too. Careful calculation shows that Cl2's rate of diffusion under these conditions would be 0.052 liters per minute, significantly slower than helium. This, of course, is reasonable because Cl2 is much more massive than helium. Graham mainly studied gases passing through orifices in a barrier. But gases aren't usually trapped with an orifice and a barrier. They're usually able to just move freely. So how can we study their motion under those conditions? When gases are allowed to move freely, they tend to move from regions of high concentration to regions of low concentration. In a sense, they move away from places where they're crowded and toward places where they have a little bit more elbow room. The difference in concentration between 2 points is called a concentration gradient, and it's kind of like a hill that matter rolls down, always moving from high to low. Gases spread out like that until they've dispersed evenly throughout the available space. This process is called diffusion. Now, it's important to keep in mind that the particles in a gas don't work together somehow to move in a specific direction. Remember those kids making their way down the hall? They all know where the lunchroom is and they're hungry. So even though there are a lot of distractions, they move purposely toward their destination. Gases, on the other hand, only appear to move in a specific direction. It's really just random collisions pushing the molecules apart, thus making them spread out in every direction. In other words, the gross eggy gas that I smelled earlier didn't travel just toward my nose. Its particles spread out in every direction from the eggs, and my nose simply noticed the ones that happen to have spread in that direction. Because diffusion is completely free movement, calculating the motion of individual particles becomes even more complicated. Now, we're not going to get into the super complex mathematics of all these collisions, but it is possible to make decent estimates regarding the net velocity of gases simply by disregarding the collisions and applying Graham's law of diffusion for diffusion as well. Here's how it works. This is a simple acrylic tube, nothing fancy. On one side, we have a cotton ball that's soaked with concentrated ammonia, and on the other side, a cotton ball soaked with concentrated hydrochloric acid. is why we're doing this in the lab and not at my desk. Both of these substances are very smelly because they're getting off lots of the fumes, or in other words, a lot of the molecules in the liquid are being released in gas form. When we put the cotton balls in a glass tube and close off the ends, those gases continue to spread, but now they have nowhere to go except farther into the tube. Fun fact, ammonia and hydrochloric acid react together readily to form a solid ammonium chloride. That's a precipitation reaction, but this time it's happening in a mixture of gases. See that the ammonium chloride is a solid at the temperature that forms a superfine white powder with the two gases between the two. So we're going to tell exactly how far each gas traveled before they meet. Let's try to figure out what that's going to be. First though, remember that Graham's law is only an estimate when applied to diffusion, but it's a good enough estimate to work for our purposes here. The molar mass of ammonia, which we call gas A, is 17, and the molar mass of hydrochloric acid, gas B, is 36. If we plug those into Graham's law and set hydrochloric acid's rate of diffusion as 1.0, since we're only looking for a ratio here, we'll find that ammonia's rate of diffusion will be about 1.5 times as fast as that of hydrochloric acid. That means that the ammonium chloride should form about 3/5 of the way down the tube from the NH3 and about 2/5 of the way down from the HCl. And there it is. See that white cloud? That's the ammonium chloride powder forming. It'll eventually settle on the glass, but it's so fine that even the tiny currents that occur as the two gases mix are enough to toss it around a little. The ammonia has indeed moved through about 3/5 of the tube. Meanwhile, the hydrochloric acid has only traveled through about 2/5 of the tube. So we've proven now that Graham's law, as an estimate at least, works. The distances that the two gases traveled were indeed proportional to their molar masses. Makes sense. That's one of the cool things about science. It always ends up making sense once you know what you're looking for. And that's it for this episode of Crash Course Chemistry. Thank you for watching. If you listen carefully, you learn the difference between the net velocity of a gas and the average velocity of its particles, and that both things have a lot to do with the mass and kinetic energy of the particles. You learn about fusion and what Thomas Graham's law of diffusion tells us about it, and how the law of diffusion can also be applied to diffusion, but not as reliably. But the collisions that occur among the particles of a gas have a huge effect on both its motion and our attempts to calculate it. You learned what a concentration gradient is, and finally, you learned how to do a precipitation reaction with gases. This episode of Crash Course Chemistry was written by Edie Gonzalez, who I have to commend for.
Okay. No, sorry, stay here. Okay, good. You were looking like you were wanting to wander, and I'm like, no, sir, we're not wandering. Come on. There we go.